Let's wait 3 minutes more, I think, and then we can start.
Okay, so just for my information, all are from Cranfield Mechatronics, or
Uh, so we have students who have gotten the offer, confirmed offer from Cranfield. Then we have lecturers. We have few externals as well.
okay,
Mostly from Cranfield and around.
okay, and all are from AVIC, automotive department.
And
Yeah.
mostly, I would say mostly.
In our
Yeah.
case, me, Jorge, Yongmin, Vib, and the others are from Connected and Autonomous Vehicle Engineering.
Very good.
Okay.
This is the first year that's this course is launched.
Yes, it's the
Yeah.
first year.
Okay, it's very good. And there are some activities in aerospace, and there are very good capabilities and knowledge. But in term, mainly for UAV and things. But yeah, there are very good guys there. You should join with them as well. Invite them to join your association. This is a very good thing.
Yes, we wanted to do something together with them, perhaps later in April or May.
Okay, so let me to check my my screen. It's Zoom. I don't know how to share my screen. Just see.
Dr. Soltani, is it okay to record the session?
Yeah. Yeah, we can record.
Okay.
I don't think there's too much confidential. No. Okay. Yeah. So can you see my screen now?
Yes.
Yeah. Okay. So I will start quickly with the kind of introduction about the company and some of our activities within CAN Engineering. 2 slides about myself, and also then I will start the main presentation, which is about the interoperable simulation and distributed simulation concepts. Okay.
So I think it's 6:05. Guys, should we start? Narendra?
Yeah. Okay, so just see if I go to full screen. This is now full screen, yeah?
Yes.
Okay. Okay. This should be changed to 21. Sorry. Okay. So, shall I start?
Yes, I think we can start.
Okay. So, thank you very much for having me in this session. And as I mentioned, sorry, the date of the slide also is not good, right? So anyway, so I will start with kind of introduction about myself and about my company. So as you may know, I've been at Cranfield for about 10 years, and I've got my PhD from Cranfield as well. But before that, I was working as a mechanical engineer. My background is mainly in mechanical engineering, but from the beginning, I was involved in simulation domain, CFD, finite elements, and my bachelor and master topics also was in this domain, but mainly in mechanical engineering domain. So before I joining Cranfield in 2010, I was working in automotive industry for about 16 years. Then I joined Cranfield to start my PhD in 2010, and from 2000 I think 12 or 13, I joined the team as a research fellow and then lecturer. So my last role at Cranfield was lecturer in automotive department. So in total, I have more than 27 years or more experience working in automotive domain, both in industry and in academia. So and I've been involved in so many projects, more than 70 projects so far. So, and because of my background, I have a kind of mixed understanding and knowledge about the mechanical engineering, controls, electrical, electronic, software. So a truly mechatronics expertise. So it might be of your interest. I just included one quick demo about the group project. I was the module leader for group project for I think 3 years, and this was one of the project because you mentioned about your group project. It was more or less the same concept in 2017. I worked with the students to design and develop autonomous parking function. So from scratch, so they had to work on a offline modeling and simulation, and then they implemented their own algorithm. They have freedom to select and choose which algorithm and which way they design this autonomous parking, and the aim was to design a kind of autonomous parking system into the car park, for example. So the vehicle should wait until give the permission and then find the free slot and do the auto maneuver for auto parking. So after the implementation in this prototype phase, they had to implement their system on a kind of autonomous pod from transport system catapult. So they had to implement this in a real vehicle and do the same maneuvers using ROS, and the whole project was 3 months. So it was very challenging, yet very rewarding. So all enjoyed from the project. Yeah. So anyway, just a very quick introduction about CAN engineering. So I left Cranfield early 2019. So now is about 2 years that I formed my new company, and I started with a small team. Now we have a 6 or 7 persons, 6 full-time and 1 part-time in my team, and we were involved in on so many interesting projects, especially at Millbrook. Thanks to Millbrook Proving Ground that provide us this opportunity to work on this environment. So we design and develop the whole simulation environment for the test and validation of autonomous vehicle and ADAS system at Millbrook. And we had some other project with some companies, I can't tell the name, but now we are growing, and we started to look at other markets, including the US and EU. So in summary, we are a kind of small yet very agile team, expert in design and development of a simulation environment and simulators and hill rigs. for different applications, including hybrid electric vehicle, ADAS, and autonomous vehicles. Before CAN, I was working at Cranfield and designed several hill rig and implemented several hill rig for hybrid electric vehicle, chassis control system, brake, power steering, etc. At Cranfield. These are some of the projects that I mentioned. And this is one of the projects that we did at Millbrook. It's about the creation of the whole simulation environment. And this was the start of thinking as a kind of a distributed simulation environment. And now we have a, let's say, the most advanced simulation facilities in the UK for test and validation of autonomous vehicle and ADAS, including several hill rigs and simulators, and a full vehicle simulator, all designed and implemented by our team internally, and a wide range of softwares are integrated with this facility, and a range of hill rigs for sensor in the loop and vehicle in the loop. There are so many other activities currently running at Millbrook. Also, we were very privileged to be invited and engaged with this Zenzik project, which kind of continuation of our initial work at Millbrook. So now we extended our capabilities and expertise to cover other testbed within the UK. I will go into some details of this project, and we are now at the final stage of this project. We completed and finished this project and demonstration, and hopefully you will join this event at the end of the March. So we'll give you the full picture of this project, which is very exciting, and to some extent is unique in the world. So, and the aim was to integrate it 3 testbed within the CAM testbed UK, namely Millbrook, SMML in London, and WNG in Coventry, to form a kind of distributed simulation environment. I will give you more detail later. Just recently, we officially recognized as one of the CAM creators by Zenzik. So now we are part of the CAM testbed and considered as one of the CAM creators, and have lots of contribution toward creation of the CAM testbed within the UK. So, and our vision is to be the forefront of advanced simulation technologies and become one of the global leaders in this market, and create a strong and long-lasting relation with the top companies, OEM companies, and test centers within the UK and globally. The area that we are currently covering is more about the advanced simulation services and simulators. Also, we started to look at some new capabilities, including extended reality, VR, XR, and so to include into this simulation domain. So this is a very quick introduction about the company and myself. So, but the main topic of this presentation is about the interoperable simulation. So, what is an interoperable simulation? So I will try to start from very beginning, step by step. We'll go through the concept of interoperable simulation and distributed simulation and why it is important. And we do believe that this is the future trend in the simulation domain, especially for connected autonomous vehicles. So this is a more about the having a kind of systemic approach or systematic approach toward the simulation. So in this concept, we try to look at the simulation as a service, as a system, and more widely as a system of systems, and try to create a kind of an ecosystem for the simulation. So if you know about the simulation and this domain, there are lots of words and lots of areas and tools and concepts involved in this domain, from driver in the loop and driver behavior, vehicle dynamics, actuator dynamics, sensor model, localization, environment, etc., etc. And there are lots of algorithm involved, for example, for control, perception, localization, and in terms of the real-time tool chain and the rigs, for example, vehicle in the loop, hardware in the loop, sensor in the loop, etc. So this is just a few of the domains and topics that are involved within the simulation, and it's a truly complex and comprehensive domain. So from the beginning, it looks very complex, and it's very hard to cover everything. So we try to apply some kind of system engineering concept to approach this complex environment, because without this, it's you get lost, because there are lots of things that are involved in this domain, and normally it's very confusing. You know, which tool, which simulation tool, which software, which approach should we apply and utilize for our simulation task. So there are so many background required to understand this, the right tool chain and the right approach for the simulation. So normally what we think from the beginning as a kind of simulation is about some kind of all-inclusive simulation tools. There are lots of softwares and package available in the market, either open source or from commercial off-the-shelf ones. Just to name a few, like a Carla, IPG, CarMaker, Scanner, Pre-Scan, and so on. So it's a very long, exhausting list of software tools available. But the main concept behind all of these tools are in a way that they try to cover everything within one simulation package, within one environment. So the main issue with this, there are lots of issues with this approach. So just give you a few examples that, for example, most of these tools are designed to focus on one area, and they are very good and strong in one domain. For example, IPG CarMaker or similar softwares originated from vehicle dynamics domain. and they are very good in terms of the modeling the vehicle and actuators. And then they try to include, for example, sensor model, traffic model, environment model, etc., etc. But the core competency of and the strength of this, for example, software is on vehicle dynamics. They try to include, for example, sensor model, but they are not comparable with some other softwares that are specialized for sensor modeling, for example, like Prescan or others. There are softwares that are very good in traffic modeling. There are softwares like RF Pro that is very good in the environment modeling, but for example, they are not very strong on vehicle dynamics and other domains. So there is no unique tool available in the market that can cover all the areas that are involved within the simulation for autonomous vehicle, and more importantly, to cover the wide range of fidelity and the details that's required for the development. Some of the software, like for example Carla, seems very comprehensive, but they are not capable to run in real time or have a kind of high fidelity models for dynamic systems and so on. So the main issues within this software are the lack of flexibility and in terms of the fidelity and the complexity of the system, and the detail and accuracy and reliability to cover the whole areas that are related to CAV simulation. So the other approach that we try to propose is about the distributed simulation, and this is fundamentally different from the kind of all-inclusive simulation tools, in a way that we accept that there is no unique software tool available that can cover the whole requirement for simulation, from the offline simulation to real-time simulation to hardware in the loop simulation. So, and we try to provide a kind of systemic approach to the simulation, and try to cover the competency and the strength of each of these tools by providing the infrastructure and the environment that can integrate. You can integrate different tools together for a specific task. And we are among the first companies who propose this approach, but there are other companies like AVL, like Porsche Engineering, and recently in the US there was some new project started with the same concept. And it might be of your interest that this concept they called interoperable simulation has been widely acknowledged and addressed for many years in defense industry, in aerospace, but in automotive this is a new. And also, for example, in defense there is a wide range of activities developed and done in this domain, but the requirements of automotive is a bit different than domain defense. For example, in defense there is a kind of hierarchy that you can define this system from top down and define all the standards, everything, and everybody should obey these rules, these standards. But there is no such environment in automotive domain. Each company, each OEM company has its own tool chain, its own way of development, own standards, and so this reality make a distributed simulation for automotive domain very challenging. but we do believe that this is the trend that sooner or later will be the main direction in automotive domain. So just for your understanding what we are talking, we mean by a distributed or interoperable simulation, I try to prepare some slides from very simple concept that and then step by step go into the details. So to begin with, we just, if you look at a kind of an autonomous vehicle, it involves a vehicle and sensors and some algorithm, etc. And the vehicle interact with the environment, with the traffic, with other vehicles or pedestrian, etc. in a way that it should work as a closed loop. So from the systemic point of view, we should look at this as a system. So this is a system that includes some traffic vehicles and other objects around the ego vehicles, the ego vehicle. So the ego vehicle is the center, and the other actors will interact with this ego vehicle, and the self-driving vehicle should understand the vehicle, should see the vehicle and perceive the vehicle and make some decision and react, and then for example the traffic will react according to the ego vehicle maneuver. So for as a kind of first step, we should divide the ego vehicle and environment so as two subsystems of the bigger system. So at the first step, we have an ego vehicle and the environment or surroundings. But inside the ego vehicle, we have a range of subsystems within the ego vehicle subsystem. For example, we have range of sensors, we have the autonomous driving software, we have actuators, and we have the vehicle dynamics interacting with the environment. Again, one step further, for example, for the sensor, we have a range of sensors attached to the ego vehicle, like camera, lidar, radar, proximity sensor, etc., or connectivities and antenna, etc. So and a GPS, and for autonomous driving software, we have a lot of algorithm for sensor fusion, for perception, for localization, planning, decision, control, just to name a few. And for the actuator, the main actuator that working for autonomous driving are steering and brake and powertrain, and the vehicle itself, including chassis, tires, suspension, and so on. So by this view, we see that the ego vehicle itself is a system, and there are lots of subsystems inside this system, and the whole considered as a system of systems. Again, for the environment, we have other subsystems for like environment, for example, rain, fog, daytime, etc. The train, the street furniture, the road, traffic, objects, pedestrian, etc. So again, the environment itself is a system including several subsystems. So to model and simulate this complex environment, we have to understand the relation between these systems. And the whole point, for example, just I give you a few examples. For example, inside the autonomous driving, there are lots of subsystems. This is just as an example. You can see the AutoWare and other software stacks that include all this inside of the autonomous driving. Also, we have to look at the development process as a kind of V-cycle, and consider the fact that we need different level of fidelity and different level of complexity and details for each development stage. For example, at the earliest stage, we need to have a very low fidelity models, more a kind of system view. But when you go into the detail, we need a high fidelity detail modeling and simulation tools. And when we want to implement this, again, we need some kind of hardware in the loop, software in the loop, and so on, to validate the system that we design. So by that understanding, we see this is a kind of is not a linear relation between these systems and the development process. So this system need to be specified and orchestrated in a way that consider the development process as well. And we have to understand which simulation tool is suitable for which stage of the development. And this is one of the main misconception that we have especially in autonomous domain, that, for example, we assume that, for example, some low fidelity simulation like Carla, etc., is suitable for the development, but this is just for the early development or even for prototyping. And when we want to look at the industrial application, and especially for the final validation, and more importantly for certification, we need to have a proper tools that cover these very serious tasks. So again, we understood that this is a complex system, but we can define this in a systematic way. We can decompose this system into subsystem and define a proper tool set that's suitable for each development stage. So this is the main concept of interoperable simulation. Also, we have to consider another factor, which is the role of the test center and the developers. So as a test center, normally we don't consider the details of the autonomous driving system, because this is a task of the system developers or OEM or tier 1 companies that develop some algorithm or software for autonomous driving. So from this concept, we have to separate the autonomous driving software and system and functions from the rest of the system. So, and this is the beginning of designing an interoperable simulation. So we separate the autonomous driving software as a kind of black box or gray box that we don't want to know the details because of the IP protection and the confidentiality. Normally, companies are very sensitive on disclosing this part. So we look at this as the top one as a kind of black box, but try to create a kind of a flexible environment for the rest of the subsystems, including the vehicle and actuators and the environment and the sensors, and try to connect this distributed system to autonomous functions. So, and when we look at this blocks in the lower block, there are a wide range of tools available for and are very good, for example, on the vehicle dynamics and sensor or train environment modeling, traffic modeling, communication, localization, location, etc. And we have to understand the capabilities of each of these tools and mix and match these software tools to cover the simulation task based on the development process. So as you may imagine, designing this kind of distributed simulation required a very detailed understanding of the capabilities of these simulation tools and how to utilize these tools and how to integrate these tools to come up with your own setup that's suitable for each stage of the development and for each simulation tasks. Okay, so with this introduction about this, and this is exactly the same concept that we applied at Millbrook, and we have now a very comprehensive set of simulation tools and infrastructure and the architecture and the middleware to integrate and glue all this together in a very flexible way. I'm not going into much detail about the Millbrook capabilities, but if you want, you can invite Peter Stoker, Chief Engineer from Millbrook, who I'm working directly with him, to run a separate session to explain about the Millbrook capabilities, which might be of your interest. Okay, so, but I'm going to give you some overview about how we applied this concept for this Zenzik project. So we have been invited to participate in a kind of initial phase of understanding the capabilities of different testbed within the CAM testbed UK a few months ago. This project initiated by Zenzik, and if you know, Zenzik is a kind of acting body under umbrella of CCAV and Innovate UK. So the government funds and activities within the CAM and CAV domain, and more specifically for CAM testbeds, are governed and orchestrated by Zenzik, and also there is a Zenzik roadmap for the UK 2030, and I also can link you to Zenzik guys to run a presentation about the CAM roadmap, which is define the whole activities and the roadmap of the connected autonomous vehicle development within the UK by the next 10 years. Activities related to test facilities, which is the CAM testbed UK. It includes 6 different test centers within the UK, including Millbrook, Myra, SMML, which is linked to TRL London, MFM, which is backed by WMG, and also IDIADA and Convex. So these are the whole capacity within the UK test facilities and capacities, not only the simulation, but also the real world testing facilities and test tracks for the benefit of CAV developments. So as part of this activity initiated by Zenzik about I think 6-7 months ago, so they started to look at the way that they can link and simulation capabilities within the CAM Testbed UK. So as part of this project, this is a long-term project, so we started to look at the simulation capabilities across the CAM testbed, and then Zenzik defined a proof of concept project about 4 or 5 months ago, and we have been selected as the technical lead of this project, and we are very privileged to have had this opportunity. So we work with the 3 CAM testbed UK, including Millbrook and WMG and SMML, on the design and development kind of proof of concept of this distributed interoperable simulation based on the concept that I mentioned for a specific simulation task, and for a specific customer as a kind of initial work and as a kind of proof of concept. So the customer of this project was Streetrone. So they have their own vehicle, autonomous vehicle platform based on Nissan van, and also they have their own software stack for autonomous driving, the full stack based on AutoWare. They call it Aslan. And this is a kind of a derivative of AutoWare, so it has all these features, and it's based on ROS. So the goal was to how we can merge and integrate some capabilities between these 3 testbeds, Millbrook, SMML, and WMG, for a specific customer, and to integrate these simulation facilities to Aslan software and run some test simulation test and scenarios as a kind of proof of concept. So again, but using the same concept as I mentioned, we started to look at the whole system, and this is the architecture that we proposed. So on the top there are autonomous driving software and functions within Aslan, and then there are subsystems for actuator dynamics, vehicle dynamics, and then it linked to road and train and environment, and then it linked to sensor, and the sensor output will feed to perception. Also, we wanted to include traffic model into this, and also demonstrate some capabilities of injecting live traffic data from a software that owned by TRL, that have some sort of capability to link with the live traffic signals at London Road with this simulation environment. And the environment that we wanted to run was the area and the streets around SMML in London. So we decided to use the SMML routes, but using a distributed simulation capabilities across CAM testbed. Together, we run this simulation at SMML route in London. Also, we wanted to link this simulation capabilities to a scenario database and have some output as a test oracle. And we designed some interface as a kind of simulation manager to set up the whole simulation So based on this concept, and these design based on the capabilities that identified within the CAM testbed between these three partners. So we started to decompose the system into AD function, as I mentioned, ego vehicle, modeling and simulation, sensor and environment modeling and simulation, traffic and intelligent transport system modeling and simulation, and pre-processing as a test scenario database, and post-processing, and a kind of interface to link the scenario into the simulation and define all the simulation parameters seamlessly. So based on this decomposition, we then define this into two domain, which is the one on top is the customer domain, and the bottom is the CAM testbed domain, similar to the base concept that I mentioned. So we try to create the whole simulation capabilities across the CAM testbed in the lower part of this table, and the upper part is the autonomous driving function and software, which is Aslan. And the software that we selected for this proof of concept was to use IPG for the vehicle dynamics and the actuator dynamics, RF Pro for the train, road, and the environment modeling, LiDAR sensor from Clitex, vSIM for traffic modeling, and a Scoot, which is the live traffic signal integrated with vSIM, and use the environment SMML environment model to use in RF Pro. So, and then the next step is to distribute these capabilities across the testbed partners, and we run two different configuration. One configuration was a distributed simulation between Millbrook and SMML. So the Aslan was you know, the responsibility of the customer, and vehicle dynamics, environment, and sensor covered by Millbrook, and the traffic modeling and simulation and the live traffic data by SMML. And also the scenario database, national scenario database owned by WMG. We define the scenario and at WMG database and retrieve this remotely. So, and as you can see, this the arrow between SMML and Millbrook means there is not a local connection; it's a distributed connection. So the bottom area is located in London, and the middle area is in Millbrook, and we establish a connectivity between these two locations. So some part of this simulation is running in London, and some part of this simulation is in Millbrook, and part of this in WMG Coventry. This is one setup that we designed and implemented. The other setup that we run with WMG was to use the same scenario and the use case and function, but with different architecture and different tool sets. For example, in WMG setup, we use the vehicle model inside RF Pro and the road and train from RF Pro again, but the traffic model simulation using Sumo, and the sensor again Clitex. So you can see there are some similarities, but there is also difference in between these two architecture, and the whole simulation again in a distributed way, but the whole simulation was running at WMG. So there was no connectivity in terms of the real-time simulation between WMG and the rest. So I will give you the reason, why we selected these different configuration and what we want to demonstrate. Also, as part of this activity, we developed a kind of simulation manager. So we can get the simulation scenario data, and based on the scenario file using SDL language, we set the whole simulation parameters seamlessly. And this is very, very important because when you want to run this in a kind of closed loop manner, and you want to run, for example, millions of simulation with a variety of scenario, you can't run this and set everything by hand. It's not possible. So you need some kind of interface and the supervisory software to set everything based on the defined scenario. So we also developed this internally at CAN. So all these interfaces, the interfaces and the architecture and the implementation, everything covered by mostly by CAN engineering team, and also Millbrook and WMG and SMML team. So regarding this, these arrows are just about the kind of define the relation and the data flow between these subsystems. But in terms of the architecture, you may notice that when we have different architecture and different combination and configuration, it's very, very hard to maintain the system in a way that it would be flexible and expandable. And one of the goals of this project was to define and propose an architecture, a simulation architecture that enable future expansion in terms of the flexibility, expandability, and modularity of the architecture, to have a flexible environment based on different use case and configuration and combination. So as part of this project also, we work on the simulation architecture. Again, for traditionally, because this interoperable simulation and distributed simulation was not a very main concern within the automotive domain, there were no activities exist in terms of the defining a proper architecture for this distributed simulation. And normally the solution that are available within the automotive domain is based on local APIs or FMI, FMU type of connections between and glue between different softwares, that these solutions are exist. But the main challenge and limitation of this ad hoc integration, or let's say point-to-point integration or pairwise integration, is in the fact that if we increase the system complexity and the number of the subsystems, we end up with a very complex and complicated architecture that's almost impossible to add more and more future subsystem and feature to the system. And if you want to change this, it's very, very hard or almost impossible. So it's not expandable. As part of this project, we also work on a data-centric middleware, and the concept that we propose is to design a middleware, a data bus that you can connect all this software to this data bus, and the data flow within this data bus using DDS technology. But there are other solutions also available, but we identify DDS as the best solution for this middleware, and we design this DDS middleware and all the APIs and the interfaces between these softwares to propose a kind of a middleware and an architecture that will be expandable for the future. Then in the future, if the other testbeds or other companies wants to join to this ecosystem and to this interoperable simulation environment, it's easily possible. And also there are lots of features within this middleware solution, including the real-time capabilities and a very precise control on the real-time capabilities of the simulation, which is very important if we want to include real-time systems or simulators or hill rigs to this simulation environment. And you can define lots of parameters they call the quality of service, in terms of the reliability, in terms of the latency, in terms of the security, and so on. So you can define all this data flow within this data bus very precisely and in a very strong way to manage the data flow between these softwares. So we designed this and proposed this architecture and implemented this as well as part of this project. And this is the final architecture of the system that we developed at CAN. So it's based on the connectivity between the test beds, and then on top of that, there is a DDS middleware, and on top of the middleware, the CAN simulation manager within the DDS, and it's an interface between the DDS middleware and the individual softwares or subsystems using APIs inside the DDS. And then we integrated these subsystems, for example, for vehicle dynamics using IPG CarMaker or RF Pro or vSim, the National Scenario Database, Sumo, Aslan, which is based on ROS1. So we designed the bridge between ROS1 and ROS2 to DDS as well. And this is the full picture of the system that we developed within 3-4 months. And then these systems, they also work integrated with, for example, vSim integrated with ITS Scoot TRL to feed the real signal data, light signals. Also, for example, RF Pro at Millbrook is linked with vehicle simulator, and at WMG is linked to their own 360-degree simulator at WMG. And from Aslan, we connected this software to the real vehicle. So we provide a very comprehensive distributed simulation environment, and very capable to run the real-time distributed simulation. And as I said, the architecture is expandable and modular, so we can add more and more softwares or hill rigs, simulators in the future. And all are sit based on the connectivity. So we established the connectivity between SMML and Millbrook, a dedicated line between two sites. But because of the time shortage and some other reason, we had no chance to add this connectivity to MFM. So we decided to run the MFM simulation setup as a kind of separate and standalone. So at that stage, I would like to give you a kind of a definition of interoperable simulation and different options within the simulation, interoperable simulation. So this is there are lots of definitions available for the simulation, but this is the definition that defined by Zenzik, and we accept this, and we think that this is a very good definition. So for interoperable simulation, we have three options. The first option, we called it interoperable model, means that we have this capability to exchange the model between different sites, between different CAN testbeds, or different partners within a distributed simulation, which is the first capability toward the full interoperable simulation. Because if you can't exchange the model or make them interoperable, you can't work on a kind of interoperable simulation. And for that reason, there are lots of standards defined and or are under definition at the moment. For example, open CRG, open drive, open OSI, open simulation interface, and so on. So these are open term, means that we try to the whole industry now working in a way that try to make the models interoperable with the common standards, that we can exchange the model to some extent, or at least can have the capability to make these models interoperable using open standards. Because one of the limitation at the moment is is in the fact that, for example, if you develop a model in IPG, it's not suitable or understandable by, for example, FreeScan or other softwares. So unless we come up with a unique standard for modeling, how we model the road, how we model the vehicle or sensors, etc., we can't achieve this interoperability. And there's a huge activity now started in automotive domain to define the open standards to enable this interoperability for model exchange. The next capability on top of this is we call it interoperable simulation. Means that are we capable to run the same scenario and the same use case, testing the same software, but with two different simulation setups within the interoperable simulation. And by this project, we demonstrated that, for example, we use the same software, Aslan, for example, and the same scenario and the same use cases and ODD, etc., but with two different setups, simulation setups. One within WMG, and one is between Millbrook and SMML. So this is also very important to be able to run different the same simulation task, but with different configuration of simulation tools. And the importance of this is in the fact that, if you remember, I mentioned about the V cycle. So if you have this capability to run the same simulation task, but with different configuration, it gives you or prove that you have this flexibility to configure your simulation system as a whole with different level of fidelity and suitability to meet the requirements of the development process. So if you want a low fidelity, simple simulation, you should be able to run the same task or scenario within a more complex simulation setup in principle. And this is the definition of interoperable simulation or simulation interoperability. And the third option, which is the more comprehensive one, is a distributed simulation capability, in a way that can we distribute the simulation subsystems and tools across the different sites and different locations to run the same simulation, which is the full capabilities and the true benefits of the interoperable simulation is within the distributed simulation, in a way that you now link up all these capabilities across the CAM testbed UK or beyond, even, for example, in the US or other places, to run a simulation. For example, link your simulation tool to a powertrain rig or vehicle simulator or other places, and do this distributed simulation, which is very, very challenging, but very powerful and promising. So we demonstrated that this setup and all this project output cover all these three options and modes of simulation operability as a proof of concept. And now we are, I can say, the only place in the world that have these capabilities. Now we are looking forward to extend this proof of concept into more like a product level that can be used by a wide range of customers and industries across the CAM testbed UK as the next phase of this project. So this is just few examples of the simulation results. Is a very, very extensive, but just to give you some few examples. These are the models that we developed in RF Pro for the for SMML route, you know, in London, and it was based on the original model that provided by SMML in 3ds. So we worked together to develop this model in RF Pro with all the textures and the details based on the original model provided by SMML, and it's based on the laser scan data and the 3D mesh. So these are all the buildings and all the roads along these routes around the SMML, now modeled in RF Pro. And also we modeled the vehicle from the visualization in RF Pro, and also the vehicle dynamic model in IPG, and also in RF Pro. So in a way that when the vehicle is running, this is just the visualization is running in RF Pro, but the vehicle model is in IPG, and the sensor is from Clitex or other software. So it's a truly distributed simulation. Is not just one software. So we also, as I mentioned, we integrated the simulation with the traffic modeling, and also to the traffic signals from London route. So this is inside the RF Pro, but it is linked to vSIM for the traffic modeling, and the vSIM also linked to Scoot to get the real signal data for the traffic light. So, and the traffic light are at Millbrook in RF Pro are activated based on the data from the London road and to the traffic simulation and to the RF Pro in Millbrook. So it's a very amazing capabilities that you can not only link different simulation tools together. For example, the right side is vSIM for the traffic, and the left side is RF Pro for the environment and the road, and it's linked with IPG for the vehicle dynamic, but also the live traffic data can feed into this simulation from London Road. So, and we run different scenarios, and as I said, based on this scenario was defined as a kind of some examples in using STL language, and the STL file was uploaded to National Scenario Database in WMG Coventry, and we use this scenario in Millbrook to set up the whole simulation. So the data the scenario file is located somewhere else, and this CAN Sim Manager was able to define the whole simulation parameters, including these ego vehicle, pedestrian, how they triggered, how they behave and react, and so on, and all linked to RF Pro for the environment, the vehicle model from IPG, and also to Aslan for example, perception or planning or object detection, etc. So all this data created in simulation using this distributed simulation environment, the point cloud data of all these buildings and the road was created at Millbrook, and we kind of benchmark this data with the real sensor data recording a real vehicle from this route, and it's very close match with this point cloud data for the path planning and the ground truth data creation. And then we implemented this, for example, path planning or object detections based on this synthetic point cloud data in simulation, running the Aslan autonomous function in ROS. So this is the very brief of some of the simulation results. But beside of for me, this simulation result is just a very brief demonstration of this capability. The more interesting part is that the whole simulation is in a distributed way, in a kind of interoperable way, with lots of softwares involved and work together to achieve these results. And this is a truly first class, world class implementation and system and architecture that open up lots of new capabilities and possibilities to include other software, tool chain, simulators, hill rigs, etc. Into the system. I didn't include, we also link this, the whole architecture, the simulation setup to the real vehicle at Millbrook using the Millbrook vehicle simulator, and also would replicate this in vehicle simulator at WMG. So it's not just about the desktop simulation, but also including the vehicle in the simulator and vehicle in the loop. Yeah, so that's it. Any questions?
Thank you so much, Dr. Soltani. I think the presentation was very pictorial and in detail, because at least for me, this was a new topic, and I think I have a basic idea of it. So thank you so much.
I perfectly agree. I found it really interesting, and I never imagined this kind of approach to simulations. I think it's something completely new, and it's been very interesting to me to see how distributed simulation can be performed. So thank you very much
Uh,
from my side.
You're welcome. You're welcome.
we can drop questions in the chat,
Sorry, I can't
or
see the chat. Can I close this um, share so I can see the chat box? Okay.
okay. So if yeah, before somebody does it, so I'll ask my question. So like you mentioned about how RF Pro can be used to simulate the environment. So there are a few things which are basically uh, physical. We may call it as physical things like the temperature is there, or if it's raining. So are those detected by the sensors and then it's fed into RF Pro and then it is simulated? Or I mean, basically, how do we simulate something that has a physical that is physical and basically
So if you are talking about the environment like rain, fog, or light, for example, daytime, night, etc., all these capabilities within RF Pro, but at least at that stage, there is no such capabilities to include, for example, temperature or some kind of detail models, for example, like finite element or crash, etc., into this. But having said that, this is, as I said, we are not talking about and not concerned about a specific software capability. We are more focused on the architecture and the infrastructure to provide a kind of an infrastructure to be able to connect different software tools in a systemic way, in an expandable way. And by that way, we are not biased toward using RF Pro, because if this software not, for example, just as an example, is not suited to our task, we have this capability to change it to, for example, Unity or other things, as an example. So in this approach, the software itself is not the primary concern, the capability of software. It's more about the designing a system and the environment and the infrastructure, and this capability to integrate different software tools in a kind of in an expandable and in a manageable way, especially for code simulation and real-time simulation, which is a very challenging task. Yeah.
on similar grounds. So basically, if suppose a car company or any OEM wants to, use it. So, like you said, this process is it can be used in various sort of environments. So can they change a particular, I'd say parameter, probably more traffic, and then
Yes.
overall things will change according to that?
Yes. It's based on there are two approaches for the simulation. One is a scenario base. I didn't include this, and there is also two different approach toward the testing. One is about the functional testing, which is very common in automotive domain, and the other is a risk-based testing, which is about the risk assessment normally for autonomous system. But in principle, one of the building block of this ecosystem is the scenario database and the scenario manager, which we will make a kind of interface between the scenario database and the simulation setup. This is a very important part of the whole system. So in the way that we run this simulation is in a way that we define the scenarios based on the different specific use case or different specific function that you want to test. And there are some languages that you can texturize this scenario in this language, for example, STL language, or now the new language is coming, is an open scenario. So you define the scenario in this language, and then the interface, the CAN-SIM manager, read this scenario file and set up this simulation environment according to this scenario. And if you change the parameters of the scenario, the simulation will change. Because, for example, if you say, I want the pedestrian to cross in that way or at that time, or in, all these parameters can be defined in a scenario file, and the simulation will be set accordingly.
Okay, thank you. So we have a few questions in the chat. First question is from Yulia. She is asking about benefits of using point-based simulation.
Okay, so point-based simulation, if you are talking about the, I don't know what do you mean by point-based simulation, but if from my presentation, what I understood is, if you are talking about the one simulation tool like Carla or any other simulation, rather than the distributed, yeah, the first step toward the simulation is using this all-inclusive simulation, because this is a simple and easy to handle and manage. But because it has its own limitations, so to some extent you can't continue using this one simulation tool to cover everything. You need other software, for example, to model the traffic properly, for example, in high fidelity with high details, for example. Or you need some software to model your vehicle dynamics in a very detailed, high fidelity. And normally, for example, the Carla or other simulation tools are not very capable to define the physics, the dynamic of the system in a proper way that you need for the detailed engineering, for the detailed design and certification. So we can say any design should be started with the all-inclusive, this type of software based on the availability. But when you go into the more details design, you need to include other softwares that are good in that domain. For example, for traffic, for vehicle dynamics, etc., or for sensor model. And this is the way that the interoperable simulation come into the place. Also, the other options that I mentioned, for example, the model interoperability or simulation interoperability, are a kind of prerequisite for the capability to change, to use a model from one simulation environment to other simulation environment and be understandable or compatible with each other. So these are the capabilities that are coming. And for example, just to give you an example, if you define your traffic routes in OpenDrive, this is understandable, this file understandable by a range of software, for example, by vSim or even Carla or Sumo, for example. But it was not the case in the past. Each software has its, so this is a trend that the whole industry try to define some common standards for modeling and then for the simulation to be interoperable between these softwares.
Okay. So we have another question from Paramjit. He says, since the architecture is aimed at real-time simulation, can it also support more real-time simulation for sweeping through a large array of scenarios?
Yeah, that's a very good question. Yes. This is we can define the parameters within the EDS in a way that it's run faster than real time, let's say. Yeah. Yes.
Okay. For now, I think we don't have any more questions, but if anybody has any more questions, we can drop our email ID and I can redirect them to Dr. Soltani. Before we go for dinner, I would request everyone to turn on the cameras so that we can take a picture.
Of course, if everybody is comfortable with doing that.
Yeah.
But so we can.
Yeah, sure.
A picture of.
Thank you, Dr. Amir. It's been a lovely interaction and very informative as well. And
Thank
I
you.
also appreciate the fact that being a mechanical engineer, you're the founder of three startups. That's really very commendable. I am also a mechanical engineer, and it's very nice to meet you.
Thank you very much. Thank you.
I hope I meet you face to face in the university.
I see Peter is in the show, and I just want to say hi, Peter. Peter Stoker, just let me to introduce him. Peter Stoker is the chief engineer at Millbrook.
Hello, Peter.
And all these activities, including this project and all this previous work at Millbrook, was done under his supervision and his kind support. So I'm very thankful of his support and very pleasant time I had during the last 2 years. It was very, very tough and challenging. We worked very hard even during the weekends and days and night. The last activity, I sent the report draft by 2 o'clock last night to Peter, and he came back early 6 o'clock. So we worked non-stop. But yeah, I should be thankful of Peter's and the whole team at Millbrook for their support. Yeah.
It's a good partnership. It's a great project. Really good presentation, and I'll maybe see some of you a bit later because one of the things I do at Cranfield is I'm on the industrial advisory board for the courses, so you may see me again.
We are very glad to have you today with us.
Absolutely.
And I recommend, Peter, if you can, you know, a separate slot just to introduce and present Millbrook capabilities, especially with this recent partnership and merger with UTAC. So it's a huge, now become a huge global company. Do you want to share this with?
We would be
Well,
honored.
I'm happy to, obviously. So yeah, let's see if we can schedule a time, and I can give you an hour in the evening and tell you what we do, because we're only 8 miles from Cranfield, and we do things other than simulation. One of the other things I look after is a very dense private 5G network and all the capabilities that we have of shipping large amounts of data at high vehicle speeds. So the current record is 3 gigabits per second at 160 miles an hour. So there's a statistic for you.
Okay, we would be honored to hear about that. So either me or Pritish, we will get in contact with you.
Yeah, please do. Please do.
Hoge, can we click a picture, please, whenever you're ready?
Yeah.
Yep.
Whenever everyone is ready.
So everyone that wants to turn on their cameras, I guess that's gotta be all of us. Okay, so I'm gonna count us down. 3, 2, 1, smile. There you go. Okay.
Okay.
Thank you so
Thank you very much for your time.
Again, yes.
My pleasure.
It was really interesting.
Thank you.
Something very new.
Thank you, Dr.
My
Amir.
pleasure.
We look forward for the next interaction as well. I'm
Thank
sure
you.
it'll be
Thank
more
you.
interesting and fascinating as usual.
Thank you, and thanks to Peter to join this meeting. I really surprised. I know. Thank you very much.
Thank you so much.
Thank you. Bye bye.
Have a nice
Have a
evening.
nice
Have a nice
Bye. Bye.
Thank you.